Thank you. Good morning. It's a great pleasure to be here. I want to tell you about neutral atom arrays and for two different applications. Some of this work is done in collaboration with Misha Lukin and Markus Greiner at Harvard. Some smaller portion of the results was done at Quera Computing. So since this is maybe not mainly an atomic physics audience, I would like to tell you a little bit about the principles of atomic arrays, how they work, and then discuss two application cases that we do in our labs at MIT. One is atom arrays in cavities to achieve strong atom-photon coupling, and then a little bit about newer results on neutral atom quantum computation with logical qubits. So how do you control individual atoms? This actually goes back, almost 30 years ago now, to work done at Bell Labs. Art Eshkin at the time, who received the Nobel Prize in 2018, was thinking about using laser beams and succeeding at using laser beams to trap particles, say in water, biological particles. And Steve Chu, inspired by that, used optical traps, focused laser beams to trap atoms. And this has been one of the workhorses of the field now for many years, to use focused laser beam to trap atoms. However, for many years the focus was not on individual particles, but rather on large ensembles. The larger the better, to make Bose-Einstein condensates, to make degenerate Fermi gases, etc. So now about 24 years ago, actually, Philippe Grangier did a remarkable experiment that was maybe not quite appreciated at the time. What he did is took a standard laser cooling apparatus, a vacuum chamber, but what he did differently is he used a microscope objective to focus the laser trap beam very, very tightly as possible to the diffraction limit inside the chamber, to a size less than a micrometer. And then he used standard laser cooling techniques to cool atoms in this region, and the CCD camera was looking at the fluorescence from the trap through the very same microscope that was used to trap the atom. And what he saw was something remarkable. He saw, and the above row are the pictures. So he saw either some fluorescence or no fluorescence. If you look at the time traces, even more remarkable is that these systems have two levels. A lower level, which you can identify with just background scattering, some background dark photons, so no atoms in the trap, and then a level that is constant and stayed there over seconds, that one can identify with one atom. So one remarkable thing is that there are these stable plateaus of one atom inside the trap about half the time, as you can see visually. The maybe more remarkable thing was the absence of other levels, right? Because you expect the loading into the trap to be a Poissonian process. You would expect sometimes 2, sometimes 3 atoms and so on. And these plateaus were completely absent. It was quickly understood that what happens is that the trap is so tight that when a second atom enters the trap, in the presence of laser excitation, the atoms get excited and interact via molecular potential that is very strong in the excited state to either form a molecule and fall out of the trap, or repel each other so that at least one, if not both atoms, flies out. So what you should imagine on this trace is very, very short instances of higher fluorescence from 2 atoms that disappear so that you don't see it on the screen. And I'll show you some data from our lab where we looked with cavities at this process and can actually time resolve it now. With that, one can, the field then, there was actually beautiful work done by Mark Safman and also in Paris on using 2 such traps to do atom entanglement and Bell pairs. However, because at the time, the loading is probabilistic, with 2 atoms, with 2 traps, it's already hard to load, and if you wanted to scale it up, it just wouldn't work. It would scale exponentially badly. So what we did in 2016 in the Harvard labs with Misha Lukin and Markus Greiner is to make not one trap, but many of these traps through so-called acousto-optic deflectors. These are devices where you send in radio frequencies and they deflect the laser beam depending on the radio frequency you set in. And if you set 100 tones into this AOD, you can make 100 traps. You can laser cool the atoms into them. You can image them onto a CCD camera, have a computer analyze the images, decide which traps are filled and keep those traps around, and then turn off the tones where the traps are empty. And so, as this movie will show, even in This was 1D experiments. Here you have 100 traps. What you see are real images of atoms in this picture. So the traps are randomly loaded, but then the computer analyzes this picture and resorts the atoms by adjusting the radio frequencies. And as you can see, as one can quasi-deterministically load near-perfect 1D lines of atoms. So now you can deterministically, we've managed at a time to load 50 atoms into these 1D systems. This was quickly expanded to 2D. So here's a 2D grid that one can sort. And again, a movie shows you it's randomly loaded, and then the sorting on the time scale of maybe 100 milliseconds or so gives you a near-perfect grid with some atoms in the lower region left over. And you can guess where this group comes from. This can be done in 3D. And you see these are now 3D structures for trapping. There's also beautiful work on that out of Wisconsin, by Mark Zafman's group. But in principle, one has the third dimension as well if you need to load more atoms. We like to work, for the moment at least, in 2D because that gives us the third axis cleanly accessed for the laser beam without having to go through layers of atoms. So we work mostly in 2D, but 3D is in principle possible for higher density storage of atoms. So this is kind of technology that was developed, in this case, for neutral atom quantum computing that I will tell you about later. But also, it is very, very attractive to, for instance, place atoms into cavities. Now, with these atomic arrays, you have the ability to place a definite atom number 1, 2, 3, 4, to tens or hundreds, but exactly a given atom number, for instance, into optical cavities. And I'll show you 2 examples. So in our system, we have 2 different systems I will tell you about. This one is a ring cavity. It has so-called strong atom-photon coupling. We characterize this by a so-called cooperativity parameter, which is about 20. It's a dimensionless number. Basically, what that number tells you, if you put an atom inside this cavity in the excited state and it decays emitting a photon, how likely is it to emit into the cavity relative to free space? And here the strong coupling is such that the atom is 20 times more likely to emit a photon into the cavity than into free space. This is achieved by basically a small waste of 6 micrometers in this case, and then light going around many times through these high-finesse mirrors. And then what we do is, among other things, so we trap single atoms in optical tweezers inside this cavity. This is an image taken through a microscope objective of a camera. But we can then also basically resolve the atom number. So what we do is we tune the cavity a little bit, tens of megahertz away from atomic resonance. And what that means is that the atom mainly acts as an index of refraction. It will shift the cavity resonance frequency. And so what you see here on the right is the transmission through the cavity as we scan a laser across the cavity line width. The line width is about 30 kilohertz. So for 0 atoms, you see a transmission peak. This is just the empty cavity. And then as we place 1, 2, or 3 atoms as verified on the camera into the cavity, then you see 2 things. One is that the dispersive shift shifts the cavity over, so you can clearly resolve the atom number inside the cavity. And if you park yourself at a given frequency, for instance here, then you can resolve just by the amount of transmission, whether there are 0 atoms, 1 atoms, 2 atoms, or 3 atoms in this case. So this gives us basically atom number resolved measurement through the cavity. What is important about this is because of the strong coupling, this measurement is quite fast. So we can resolve now on the time scale of 100 microseconds the atom number just by looking at the transmission. So this is what these curves look like. Here I show a probability density plot, transmission and probability. And what you see here is that the peaks are very clearly resolved. This peak is 0 atoms, 1 atoms, 2 atoms, 3 atoms. This is when we randomly load a certain number of atoms into the cavity without trying to prepare them. So you see that these peaks are very well resolved. This is when we do this in separate traps. And if you look at time traces, then you see interesting plateaus now. So for instance, you see, because the atoms are individual trapped, you can have 1 atom. I think this is a 3-atom state. You see sometimes events where the atomic state changes. The atom has 2 hyperfine states. One of them is coupled to the cavity, one of them isn't. So if you pump the atom to the other state, the atom either blocks the cavity or goes dark for the cavity, so we can manipulate the atom and see them in real time with a time resolution of about 100 microseconds. And now it becomes interesting, going back to this Philippe Grangier work, if we place atoms into a trap, And we look now with very high time resolution what happens in the beginning. So this is now a single trap. And what we see now here is basically up means high atom number. So we start with several atoms, and then there are very fast collision processes that reduce the atom number to the blue level, which is 0 atoms, an empty trap, or to the orange level, which is 1 atom. So you see there is, for brief times in these systems, several atoms are loaded into a trap. Then there's collisional processes that reduce the atom number in pairs or so until either 0 or 1 remain. What we see sometimes is also these events where it seems like the atom number is slowly increasing in time. This is actually not the atom number increasing in time, but that's an atom that was hot and therefore spent most of the times outside the cavity being recooled through a mechanism, cavity cooling for the experts, that makes the atom again strongly coupled to the cavity. So we see sometimes collisions, and we can resolve that now in real time, where the atom leaves the cavity, sometimes collisions where the atom gets heated out, not quite out, gets heated and then recooled. So we have now really good time resolution to verify these models that were used for the trap loading. Another experiment with cavities and arrays that I would like to tell you about, which led us to an important technological discovery, is error correction. So what we did here, this is a different type of cavity, a standing wave cavity with a little bit weaker coupling on the order of 1 cooperativity. So we placed up to 5 atoms inside this cavity, and then we were trying to use these atoms as a classical register. So we haven't done a quantum register yet, but we have 2 hyperfine states, one of which couples to the cavity and the other one does not. And we look at them and use them as a classical register, and then we want to do classical error correction. We want to look at the state of the individual atoms and then correct any errors that occur and see what we can learn about this. For this, we also developed a new method to measure the atom number. So in this kind of histogram, we have here, if the cavity is empty, then we're scattering light into the cavity. If the cavity is empty, then we have mostly 0 counts with a little bit of background with 1 count. Whereas if the cavity contains an atom, we get this histogram, which in a given time gives us about 15 atoms for very good resolution. So you can resolve these histograms. Now we wanted to both speed up the process of detection and also reduce the heating of the atoms, because as you're scattering light, the atom gets heated. So this is one of the places where we used quantum machines. We also used it for the previous experiment. In this case, we used quantum machines to tell us whenever 2 photons were detected to simply stop the light, because our threshold is between 1 and 2 photons. So as soon as we have 2 photons, we don't have to measure any longer. We just stop the light in real time within a few microseconds. And that both gives us much less heating and much faster detection. So this is a place where we use these quantum machines, and the students and postdocs really love them. They say they're very easy to use. So how did we do the classical error correction? We prepared either the 5-bit 0 state or the 5-bit 1 state, then measured. We introduced actually errors on purpose because our native errors were too small. We measured and then we reset. And in this case, I show you kind of the memory with 1 bit, 3 bits, and 5 bits. On the horizontal axis is the physical bit error probability, and then on the vertical axis, both on exponential scales, is the logical bit error probability. If we have just 1 bit, then the physical and the logical bit error probability are the same, but as you go to 3 bits or 5 bits, you see an improvement. Basically, errors get exponentially suppressed with the physical error bit probability and the number of bits. So we looked at how do the errors occur, and we found that basically we were limited by in the end by atom loss. So we measure the atom, we reset it and so on, but the atom eventually gets heated out of the trap. And so after about 10 or so, 10 to 15 error correction rounds, we had simply fewer atoms inside the trap, and the performance of our memory decayed. And this will connect to the last part where we are working in the context of quantum computing and a new system that can actually actively and in real time replenish atoms. So let me tell you a little bit about quantum simulation of computation with Rydberg atoms. This is a collaboration of Misha Lukin and Markus Greiner, but there has been amazing progress in the field, including in Wisconsin at inflection, etc. So you need a few ingredients. You need single qubit rotations. I won't dwell on that, but everybody can do kind of single qubit rotations with the help of 2 laser beams at the order of 1 part or so in 10 to the minus 4. The hard part are really the 2 qubit gates. For the 2 qubit gates, you can ask yourself, if you have 2 atoms separated by a few microns, how can we make them interact to make quantum gates between them? This goes back to a paper by Dieter Jasch, Ignacio Cirac, Peter Zoller, and Ruben Coté, Ralston, and Misha Lukin at about the same time when Philippe Granger did his experiment a little bit earlier. And they proposed that putting atoms in highly excited state could produce strong and tunable and controllable atom-atom interactions. The way it is done is one goes to a very high principal quantum number. In the beginning, people did something like n equals 100. Now the optimum has maybe shifted down to n equals 50. Nonetheless, think of hydrogen in the 50th, say in the 50s state. What happens is that the electron is very floppy. It's very far from the nucleus, so the electric field of the nucleus is very weak. And that means that quantum fluctuations in one atom can produce an electric field that will polarize the other atom very strongly. So you get a van der Waals 1 over r to the 6th interaction, just like in the ground state. But amazingly, the interaction in the excited state scales with the principal quantum number to the power 11. I don't know where else I've ever seen such a strong scaling, and this is what makes these experiments possible. You get kind of 100 megahertz-ish or a few hundred megahertz interaction strengths over optical resolvable few micron distances. And then when you put 2 atoms together and you try to excite them, then if you excite one atom, you cannot excite the other one because of the interaction, and that automatically creates a Bell state of the atoms and can be used for a quantum gate. Where are we as quantum gates? There's now a number of groups who have seen things at a similar level. We are at about 99.5% in these published data, and unpublished data, we are doing quite a bit better than that, and we're trying to push this frontier further. Why is this important? Well, because the threshold for error correction for the most attractive codes is on the order of 1%, can be even a little bit higher with erasure detection as well. So as a field, we are now below this threshold, so we can start to explore circuits with logical qubits. Another important ingredient, just to quickly show, is that we can maintain entanglement while transporting the atoms. We create a Bell pair between 2 atoms, and then we transport the atoms over distances, say, typically here 100 micrometer, simply by changing the radio frequency going into the AOD, which changes the laser beam up and down. And we find that if we don't move too fast, and the critical speed is about 1 meter or so 100 microseconds for 100 micrometers, then we see no deterioration when we do things right between the Bell state that we created and the Bell state that survives this transport. So this means that we can now not only couple next neighbors, like in fixed superconducting circuits, but we can actually move atoms, blocks as a whole, and perform now transverse gates between logical qubits simply by moving them. So we have, in principle, arbitrary connectivity. So quantum error correction is hard, and there are experts in the field like Serge Roche, whose opinion I generally I think he's a fantastic scientist. He, for instance, wrote a few years ago, he still stands behind the statement that error correction will become exceedingly difficult, is not practical. And I think Mark and we and others are trying to prove him wrong, but we'll see. But there's still skepticism, but I think progress has been very fast. Quantum error correction is really remarkable, I think, kind of theoretical idea that is not obvious at all, because in classical error correction, if you look, say, at a string of 9 bits, you just look which ones are in which state, which ones are in the other state, you take a majority vote, and then you reset, in this case, the red bits to white, because it's much more likely that 2 bits flipped than that 5 bits flipped. However, in quantum mechanics, of course, you're not allowed to do that. As soon as you look at the state of the bits, of the qubits, the whole quantum character is lost. But people have come up with, I think, quite ingenious techniques to compare the states of atoms that represent a logical qubit to each other without actually measuring the bits itself. And this is one of the favorite codes. There are others at this level, where basically you encode a logical qubit in a grid of physical qubits, and then you compare via an auxiliary atom the parity of four neighboring data qubits to one another and try to see errors. So for instance, if this one had an error in the simplest case, then depending on the type of error that it had, either the Z qubits would light up or the X qubits would light up, tell you the error. The real story is much more complicated because while you're detecting this, you are also making errors in the quantum gates needed for this. So the so-called decoding process, how to extract the information from the ancilla qubits to determine which data qubits need to be flipped, is a complicated one. But nonetheless, it's possible. And this goes back to pioneering work by Peter Shaw and Anders Steen and then many others. We detect the atom. Originally, we detected the atom simply by pushing one of the states out. Our quantum states are the hyperfine qubits, hyperfine clock states in the ground state. Originally, we pushed atoms out, but it's actually much more favorable if one can distinguish qubit state 0, qubit state 1, and the loss of atoms. We did this by adopting a technique that was originally developed by Dave Weiss at Penn State. Basically, we do a spin splitting via an optical lattice, as you will see here. We are doing a spin splitting where the optical lattice transports one of the states out to a new location. Then we turn the trap back on, and then we image the atom's position. And so now the spin gets mapped onto atomic positions, so we can detect, is it in 0, is it in 1, or is it lost? And for quantum error correction, this is very important because if you have information about that the atom has been lost, then actually the threshold for the quantum error correction codes improves generally and quite significantly. And so we can measure this, and so it enables basically this three-state detection, and also it retains the atom. And this is a picture of Rabi oscillations between two spin states that are then converted via this process into basically spin position mapping, and you can kind of see visually how here a string of I don't know how many atoms, a few 10 of atoms, kind of oscillates between the two states as you're driving the laser beam between the two states. So our vision now, and the thing that we're doing for a quantum processor is that it has different regions in the microscope plane. There's a storage region for the data qubits. There's an entanglement region if you want the CPU or the QPU, the quantum processing units. There's a readout region where you read out the ancilla qubits after moving them out to detect errors. And then there's a reservoir of atoms that we can now continuously refill because there's a small probability of loss, about 0.1% or so per gate cycle that comes from atom heating or the atoms being lost during the Rydberg gate process. So here I'll show you quickly one logical code. This is also called 1664 hypercube code. This means it's a distance 4 code. And geometrically speaking, it looks like a hypercube or a cube in 4D. But because we can move the atoms, we can kind of, we can realize any dimensionality that we want, including a 4D dimensionality. And this gives you just a flavor of how these atoms are moved relative to each other in blocks. To induce these quantum gates. The takeaway picture here is that you don't need to move each atom on its individual paths. You can move atoms in blocks for these transversal gates, and this greatly satisfies or makes it easier to run circuits because you no longer need one or more control lines per physical qubits, and that physical qubit number in the future will be very large. You need a few control lines or maybe one control line for logical qubits or blocks. I would like to show you briefly some results from Quera computing. These are so-called non-Clifford gates, and generally in quantum computing there's the Clifford gates, which can be transversally, and then these so-called non-Clifford gates, and you need both in the system to make it classically hard to compute. And one way to do non-Clifford gates is so-called magic state distillation. Here the goal is to make a state that is pointing a logical qubit that is pointing along 1, 1, 1. Now, physical qubits are easy to rotate, right? Single qubit rotations are very easy, but logical qubits are actually not generally simple to rotate because you need to manipulate many different qubits. And so at the same time to get a logical qubit rotation. So what we do is a so-called distillation process where we make multiple copies of, finite, the best that we can, but finite fidelity qubits in a certain code, and then we compare them and distill them and detect errors to make one qubit of a higher quality than before in this state 1, 1, 1. And so basically you prepare high fidelity magic states from noisy magic states through this distillation process that improves the fidelity. And this is what it looks like for the distillation for the D=5 color code. And again, what you see is that there's some good degree of parallelism. In this case, the atoms are moved in rows or maybe pairs of rows, etc. And whenever the atoms are placed close to each other, that's when a 2-qubit quantum gate occurs. So this is the team at QERA, including Sergio Cantu, Pedro Sales, John Robinson, and Nicky Jepsen. This is the results. So basically, the main takeaway here is we prepare the qubits at a level of 95% fidelity, and then through distillation, by reducing 5 qubits to 1 logical qubit, we can improve that fidelity to about 99.5. And we did this with the distance 3 and distance 5 color codes. QERA and QERA Japan, we have delivered a quantum computer to Japan, which is beginning to be operational, have open positions. So if you would like to join us here in Boston, or if you're an atomic physicist and you would like to spend a year working in Japan, please look at our website. We are really looking for people. And Mark and I talked this morning. The speed in our field everywhere, but especially at the computing companies, is really limited by the number of people we can train and absorb and go forward. So it's limited by that more than anything else. So if you have ambitions in this direction, or also on the algorithms, like to work on the algorithms, please contact us. We encourage applications. Let me finally show you how to replace atoms, because as I said, there's a little bit of a loss process. So right now, you can do about maybe 1,000 rounds before the atoms are lost, 1,000 gates or so. Here we have a new system where we are continuously delivering atoms and then pulling them out of a trap where they're not single atoms. We have tweezers and then placing them in this region, and we're maintaining 3,000 atoms in this region. Every few hundred milliseconds, we're throwing some away to bring in new atoms, but we can now already maintain 3,000 atoms, and this was after not trying too hard, and continuously replace them. Maybe the key features are before that, we were laser cooling in the same region where we were having atomic tweezers to load the atoms. Right now, we have separated these two regions. So we have this laser cooling region, which is about 40 centimeters away. And then we transport the atoms in an atomic conveyor belt. It's actually 2 laser frequencies that are almost the same, counterpropagating. If they were the same, they would form a standing wave and trap the atoms. If we introduce a small frequency difference, we can transport the atoms at a desirable speed to this new region over 40 centimeters in a laser beam, and then we use these optical tweezers to pull these atoms out, detect that we have single atoms, sort them, etc. And so maybe key takeaways are that we can, at the moment, load about 30,000 atoms per second in real time, in continuous time. By operating, maybe one more thing that I forgot to point out at the beginning of my talk, we used it also for cavities, but it's important here. One of the difficult things is that you have the data qubits in one region, and relatively nearby, over a distance of a few hundred micrometers, you have the ancilla qubits that you need to drive with laser beam, and they need to fluoresce and emit photons so that you see which state they're in. And you must somehow protect the data qubits from that light. We do that by carefully focusing in laser beams and basically trying to minimize. But the atoms, say, in the detection region, it's not shown here, but imagine this is the detection region, they scatter photons, so you have to protect these atoms. So what we found in the cavity context, what works really well, is a so-called shielding laser. So these are the atomic ground state where we store the data qubits. We apply a laser beam from the atomic excited state to another excited state on a strong transition. And with this laser beam, even with very moderate power, you can shift this level around by several gigahertz. So basically, you can kind of in real time change the spectroscopic signature of the atom by several gigahertz. And so you can make the atoms in the storage region transparent to the light emitted by, say, the atoms in the detection region without actually touching the ground state, because this laser beam is far detuned from any ground state transitions and resonant on this transition. And this method works very, very well to shield the atoms. So in some sense, we are able to change the spectroscopic signatures of the atoms in real time with this method. And that's important for the readout. So with that, entanglement is turning from a strange concept in the useful tool. We can do it. I didn't talk about clocks much, but we can use it for cavity QED context. And in quantum computing with neutral atoms, I think we are collectively as a field on a great path. We have done first experiments with up to 96 logical qubits. We are already on a very good path to 10,000 qubits. Manuel Enders has 6,000 qubits. We have 3,000 continuously reloaded. I think the path to 100,000 physical qubits is wide open. Beyond that, there are limitations that we have to think about how to do. But 10,000, I think, is a no-brainer, and I think 100,000 will be there in a couple of years. And with that, we think we can get quantum error correction at the level of 10 to minus 6 and beyond. And so it will be very interesting to see whether algorithms open up there and how to scale the system. And with this, I would like to thank you for your attention.
Coming.
You guys are absolutely amazing. This talk was kick-ass. Two questions. One is, what's the physics of the 1 meter per second speed limit? Mm-hmm. And the other one is, what's the bottleneck on a full error correction cycle for you at the moment?
These are very good questions. So the limit is not really a speed limit, it's an acceleration limit, or rather, even the time derivative of the acceleration called the jerk. So basically, as you move the trap has a maximum force, and you need F to satisfy F equals ma. So it's not actually, you can move over larger velocities as the acceleration process. In practical terms, that leads to this kind of 1 meter per second speed limit. If you make the trap deeper, you can win by a factor of a few, but it's only square roots, so it's a little bit costly. But I think it will end up between 100 microseconds and say maybe 10 microseconds or so for this kind of motion. If you use optical lattices to move, you can do much faster because the forces are much larger. The speed limit for us, and the reason why we hadn't focused so much on the motion, is really the detection of the state, the ancilla readout. That one is at the moment 4 milliseconds for us. We are trying to push it down to one millisecond or so. So everything else is much faster. The quantum gates are hundreds of nanoseconds. The 2-qubit gates, single qubit rotation similarly. Even the transport is fast, so we are really limited by the optical readout for error correction. And so we'll have a clock cycle, I think, on the order of a millisecond for the foreseeable future, for at least for the next few years. Mm-hmm.
Thank you. Any other questions? I have one. So what's the role of cavities in the context of these 2D arrays?
That's a very good question. There are several goals of cavities. One is you could use them for faster detection if you integrated the cavity structure with and that's the second experiment that I talked about, was along these lines. How fast can you read out a string of atoms? Of course, cavities, a camera is parallel. You can image many atoms. Cavities are serial, at least when you use one mode, but they are much faster, right? You can detect with atoms on a microsecond time scale rather than a millisecond time scale. So that's one role. The other one we are interested in is eventually we'll run into a size limit for the modules, right? It will be 100,000 qubits, maybe 1 million qubits, but there will be a size limit. So if you want to think further into the future, we really need to connect modules to each other. Other platforms need to do that much earlier, like ions, for instance. I think they need to do it much earlier. So we are really looking at how to transport quantum connections, quantum entanglement. The obvious answer is photons. I think maybe Mark will talk about entanglement rate between two cavities. So forward looking, I think at some point we will need cavities to connect modules through a true quantum connection.
Thank you.
All right, so first, thanks for a great talk. This was very interesting and inspiring. So you had this graph where you showed the logical error is function of the number of iterations, right? Where you had n equals 1, 3, and 5, I believe.
Right.
And then the lines kind of started converging as the number of iterations increased. So I'm not. And then you mentioned that it's because of atoms escaping.
Right. So at that time, we don't have any more 5 qubits.
Yes.
We have only 1.
So then I wanted to ask one, if atoms would not escape, then how these graphs would look like, and two, what dominates the escape of the atoms? Is this related to the actual measurement, or what is it?
Very good question. So in this case, it was related to the actual measurement. It was a loss of maybe 0.5% or so per round. If we were replacing the atoms, it would perform much better and would be just, P over pre-threshold for quantum codes to the distance over 2. So basically, in these graphs, we wanted to learn what happens, and it's interesting that the first thing you see is actually the loss of atoms reduces your quantum register. And that convinced us also that we had to work hard, among other things, on the replenishment, that it wouldn't be practical without replenishment. In some experiments, we have used at Harvard a fixed reservoir, so we load more atoms than we compute with, and then replace those. That already works, but again, it's only finite. So we really need this continuous solution, I think, if we want to do deep circuits, and that's what this experiment taught us.
Thank you.
Okay, thank you very much.